Hi everybody. Let me wind the music down here. Welcome back to Chem 131. It is Wednesday, week 5, which means that after today, we're halfway done with the quarter. What? Where did it all go? Who knows? Time is an illusion during the pandemic. Ooh. But what's not an illusion is Maya. I swear I just heard her. There she is. She's hiding. She was very disruptive during all my classes yesterday, and so she got chased off with the squirt bottle. I have no doubt that she'll be back in just a little bit, though. In fact, I can hear her crying in the background. Oh, poor thing. Poor Maya. All right. We already did this. This was yesterday's, the last thing we talked about yesterday was doing the Benedict's and Tollens tests. So make sure that you are able to identify molecules that have the appropriate functional groups to react with those. And remember that for Tollens, it is just aldehydes. Any aldehyde will do. And for Benedict's reagents, it's one of these three. So aldehyde, carbonyl, aldehyde, alcohol, or carbonyl alcohol. All right. Let's do some more reactions, and then we'll be mostly done with the chapter. And that's really all I had planned today, so. First thing we want to do is talk about what's this reaction called reduction? Well, we've been doing oxidation all along, haven't we? And I've sort of told you what oxidation is. It's, to add oxygen to things, or you remove hydrogen, things like that. Well, you could do the reverse. You could just put the hydrogen back, and it's called reduction. We've actually already seen the reduction reaction when we did this with double bonds. When you add hydrogen and platinum or palladium or nickel, you got a saturated alkane from your alkene. Now, if you have any double bond, it turns out you can do this, particularly if you have a catalyst involved. Benzene is a little bit different. Benzene resists most reactions, unless it has very specific catalysts. But other double bonds are pretty much open game. So that includes C double bond O. So if I take an aldehyde, and I react it with hydrogen, and I have a catalyst, what ends up happening here is, let me get the pen. So I'm going to add H across the double bond. One of them's going to go here, one of them's going to go there, and I'm going to break the bonds. And so I end up making an alcohol here. Not only is it an alcohol, it's a primary alcohol. And if I do this with a ketone, I get more or less the same result, except instead of a primary alcohol, I end up with a secondary alcohol. So these two bond, and then these two break. So a reduction reaction is the reverse of an oxidation reaction. I don't actually remember what the shorthand is for that. So like for oxidation, we put O in brackets. For a reduction, I don't think we put R in brackets. It might be H. But probably just what you want to look for is, oh, I'm trying to add H2 with platinum. So that's a really simple reaction to study. So just to test your knowledge here, I want you to give me the product of this reaction and also type its name in the chat, because you should be able to name the result of this. So go ahead and do that. Do the reduction and type the name of the resulting product in the box for me so I can see it. We'll go over the answer in a second. All right. I see someone is awake in the chat, so we'll go over the answer here. So with our reduction, boop, 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 boop. Connect my H's to each of the ends of the double bond and then break the double bond and the H bonds. So I would get do, 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 which would be 3-pentanol. Very good. I don't know why I was going over there to erase this to do that, but there you go. All right, here's some more. Now, I put a little note down at the bottom there that whenever you see a benzene ring in one of these reactions that adds across double bonds, just ignore the benzene rings, because benzene doesn't typically undergo addition reactions. And the reason for that is it needs a certain specific catalyst. So platinum doesn't work with it. You need something unique. And what the unique catalysts usually are is something like this. Stuff like this. Like they're ionic compounds, and there's something very specific about them that makes benzene react with it. It's called an electrophile, and what that means is that the catalyst loves electrons, and benzene has electrons in its double bonds here. So those double bonds actually react with the catalyst. And that's what initiates the reaction. We don't really do nucleophiles and electrophiles in this class. So just pretend that you didn't hear those words, because I don't want you to get them mixed up with things like electrons or whatever. So do these two reductions. You don't have to name these, but I do want to know what the products are. It's kind of impossible to type the names of these in the chat, at least the second one. But go ahead and do these. I'll just give you 5 more minutes to do the reactions, and we'll go over the answers together. Yeah, don't worry about naming the second one, because we haven't talked about what to do for benzene when there's an extra carbon coming off of it. Because, like, it would be a phenyl group if there was actually a chain, but it's sort of an exception. I think it's called benzyl alcohol instead of phenol. Don't quote me on that, because I'm not sure if that's the right name for it, but that's okay. Let's go over the answers here. So, do 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 do. There you go. That's what you should get for the first one. And then we'll do the same thing here. Do 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 do. So I got benzene, and then boop, boop, boop. There you go. So this one over here, this is just benzaldehyde. So that's actually a really common compound, and I believe that benzaldehyde is responsible for the, like, almondy flavor, I want to say. Let me look that up real quick. Because a lot of aldehydes end up having familiar flavors that are... Let's see here. Yeah, bitter almonds. So that's just a little fun fact. All right, let's keep going. Oh, the fun reactions. Okay, so these reactions here are kind of weird. However, they are very important for carbohydrates. So that's why they're put in this section here. So when you have an aldehyde or a ketone and you have an alcohol mixed in there, the two can react because C double bond O carbonyl groups are reactive to all sorts of interesting and unusual things. So the first one that we're going to look at is this. When you put an aldehyde and an alcohol together, you get what's called a hemiacetal. So aldehyde with alcohol makes hemiacetal. And so what is a hemiacetal? And hemiacetal is the result that when you mix these two things together, the following happens. So I'm going to take the H, and the H is going to go right here. And then I'm going to take this OR group, and it's going to go here. And then I break a double bond. I'm also breaking the bond between the OH here. It's just not written. And the result that we get is we get a alcohol, and it has an OR group on there too. So this is a hemiacetal. So we've got an alcohol and then an OR group. The double bond from the carbon-oxygen goes away. It's gone. We've reacted across it. You can think of this as just like our addition reactions across the double bond, where I add the O end to the carbon and the H end to the O. Now, there's an interesting thing to note here. You might notice that, hey, we haven't really had an arrow like this before. Turns out hemiacetals are not exactly that stable. And so if you make a hemiacetal and it bonks around, there's a chance that it can revert back to what it started as. However, if you make the hemiacetal and then you react it with something further, you get a different result, and then it's stuck like that. And we're actually going to see that you can take a hemiacetal and react it with another equivalent of the alcohol, and you make an acetal, and that's stable. So let's look at that. So here's my hemiacetal. Notice that I've recolored the stuff. And the reason I've recolored it is because now I'm going to take my alcohol here. This is the same alcohol as before, so note that it has the same R prime on it. And then my H is going to go... Oops, I have the wrong color. My H goes here with H... Or, sorry, OH up there. I'm going to make H2O, so that's going to go away. And then my OR takes its place. So the bond I'm actually breaking is this one. And I break the bond between the H and the O also. So now I get something with two OR groups on there, because there will be this one there, and then this one that I'm adding on top. Now, in order to do this, the second addition needs a catalyst. It needs some sort of acid. The reason it needs acid is because it's actually the catalyst putting this H up here. But as far as our mechanism is concerned, to like remember what's going on, this is adequate. Now, when you get an acetal, you get a stable result that does not tend to return to the initial products. Or, sorry, initial reactants. So, the general process that we just did in this reaction, so we started with an aldehyde. And then we got a hemiacetal. And then we got an acetal. So on that giant list of reactions that you have there, you can write aldehyde plus alcohol makes hemiacetal plus alcohol equals acetal. Or something like that. And then for ketones, it's exactly the same thing, but we give different names for it. We say ketal and hemiketal. So let's do an example. So I'm going to give you 1, 2, 3, 4. So this is butanal. And I'm going to react it with methanol. Butanal. I just wanted to write the name on there because hopefully we haven't all forgotten about how to pronounce aldehydes. Teehee. What would the product be? So first write out the ROH, which in this case R would be CH3. And note that I have indicated I want the final product after multiple steps have happened. So I have all of this, not excess is what I wanted to write. I have all of the methanol that I want because I put it on top of the arrow. It's a catalyst. So go ahead and try and do this because Maya just arrived. And I need to... Oh, no, she's running away. She's like, please follow me. So maybe I should do that. Go ahead and try and predict the products of this. Do the first edition and then the second edition. And I don't know if you can hear her. But, yeah. I'll be right back. All right, so I'm back. Maya is here too again. Okay, so we're going to do step 1 down here. So we're going to add our CH3OH. I don't really have a good way to draw this, but the O goes here. And the H goes here. We break this bond. So that would be the first addition. So we'll go. So first we'll draw the butanol part. There's my H. So I got OH, OCH3. And then we're going to add the second part of it. So I will put... We'll do that. The O goes here. And the H goes here. And I break this bond. And so then I still have this OCH3 down here. And I have a second one up here. Now I do also make, so this right here is just water. However, we don't really care about the inorganic products because this is organic chemistry. So you don't have to include that in your answer. It's nice to note that water comes out. If you were actually doing the synthesis, you would probably want to know that there was water coming out of your reaction in case water could react further with something. And then you would know, oh, I should put something in there to capture the water, like a desiccant or something. All right, so that should be the result, and that is what we get. So we're all set. Now, you might remember before when I showed you those molecules that look like people, and like you had the baker and the Texan and the kid or whatever, and they were molecules that look like this, and they had like O's here, and then you formed the bonds from here. That's kind of what these molecules are. So here you have this O and this O, which you could use to make bonds like that. So if instead of adding CH3OH, I added this alcohol, I would get that reaction. Why do you add CH3OH more than once? Because I asked for the final product of the reaction after multiple steps here. So if you see me say multiple steps, then you're going to add methanol multiple times. The other way that you can tell that that's what's going on is because when you put something over an arrow, what that means is that either this is the solvent or is in excess. And pragmatically speaking, what that means is that you have tons of this, all that you could possibly need. So when you put something over a reaction arrow, that just means this is in abundance. That's what that commonly means. So because it says multiple steps, this is the primary way I'm trying to indicate this. I want you to do first the hemiacetal and then the acetal. All right, let's do another example here with a ketone. Ketones react exactly the same. The only difference is that instead of having that H hanging out from the aldehyde, it'll just be whatever the rest of the molecule is. So when we do this reaction, we're going to first get a hemiketal and then a ketal. So let's do an example here. Here's my ketone. This is 2-pentanone. And I'm going to add methanol to it because we just add simple alcohols. That's our shindig. And so we're going to do the exact same thing. So we're going to add the H to the top there. If I can find the right color. There we go. Boop, there it goes. And then we're going to add the rest of it to the bottom. And I'm going to break the OH bond here, and I'm going to break this C double bond O. And so the result should be that I have an OCH3 group coming off of this carbon right here, and an OH also. So there you go. Now, just like with hemiacetals, hemiketals are unstable, and they can revert if you don't have enough of the alcohol to keep it as a ketal. But if you do a second reaction with the presence of H+, just like before, then it will stick around. So we're going to do the same thing. This OCH3 is going to go right here. The H is going to go on the other side with the OH. I break this bond, and I break the bond that holds these two together, and I get my ketal. I'm writing the water in this case, but remember, you don't need to write that if you don't care. We care about the organic products in organic chemistry. All right, so now you've seen two of these. Hopefully you get the gist of it. So what I want you to try and do here, I've written it a little bit differently now, but the end result is the same. You can see, oh, there's two of them here, so I have to do this twice, and I have this. So I'm going to go all the way to the final product of this reaction. So take this starting reactant and do the first addition and write down the product. And then take that product and do the second addition and write down the next product. Okay? So try that and let me know what you get as a result by telling me that you're done with the reaction in the chat or something. Yeah. I guess you can't really tell me because I don't know how you're going to communicate this molecule to me. But we'll go over the answers together in just a moment. All right, one more minute. We'll go over the answer. All right, let's see what we can do with this. So first of all, we're going to add our CH3OH. This guy's going to go here. I'm doing the wrong color. Hold on. So the H is going to go up here. I'll stick with the same colors so I don't get you guys confused here. And this O is going to go right here. I'm going to break the double bond, and I'm going to break the bond between my O and my H. So this will be the first addition. So let's draw the molecule here. So doot, 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 doot. So there's the first one. And then I'm going to take my second one, and my O is going to go here on this carbon. And my H is going to go on this OH. I'm going to break the bond, break this bond. And we'll get the second one, which should be... Ooh, that was bad. Hold on. Let's see here. So I got that, that, and that. All right, let's see how it matches. Doo-doo. Hey, that looks pretty good. Sweet. All right. Now, this is just neat and all. But why do we really care about... Oh, I thought that we were done with this topic. Why do we really care about hemiacetal, acetal, hemiketal, ketal formation? We're going to talk about that in the next section right here. But for now, here's some more of these for you to practice. So I've given you a benzaldehyde and... gosh, I want to call it benzophenone, but I don't know if that's what that's actually called. So I've given you these two things. Tell me the products, but note that I have given you a different alcohol for the first one. Okay, so be careful of that and compute the products for both of these. We'll go over the answers together shortly. All right, 1 or 2 more minutes. We'll go over the answers. If you aren't sure, Maya will give you a hint. Maya, what's the answer? There we go. I hope that was helpful. All right. There is currently a cat on my lap, so I'm going to see how well I can write around her. I guess we'll see. All right. Oh, I can just turn slightly towards the left here. Hopefully, if the slides advance, it's because Maya hit the spacebar. Okay, so for this, we have a different alcohol. So we need to get a slightly different answer. For the first one, I'm trying to pick the right color, but Maya's not helping me here. So I'm going to put this right there. And we're going to put the H right there. We're going to break this bond. We're going to break this bond. And the intermediate product that we're going to get is, I'm going to put it up here. So here's my benzene ring. C. Maya, why are you spinning around here? I've got the OH up here, and then down here, I've got OCH2CH3H. Maya, stop. Okay, you need to leave. Now she's trying to rub against my hand, which I'm using to hold up a cord so that she doesn't trip on it and knock over everything on my desk. So now she's got to sit on her pillow. Huh? Yeah, you guys sit on a pillow. All right, so that was the first one. And then for the second one, we're basically going to switch out this OH for the same thing. So we'll have OCH2CH3. We've got an H here still, and then we have another OCH2CH3. You're probably starting to figure out by now, oh, I just get rid of the C double bond O and stick to O, whatever my alcohols are on there, and that's exactly what you do. For the second one, we'll do the same thing that we did before. We're going to take this H, and it goes up here. We're going to take this OCH3, and it goes here. And so our intermediate product will be benzene. We've got the CH3, which is still here. OCH3. OH. And then I'm going to do the same thing. I'm going to add to this OH to get rid of it, and then replace it with another OCH3. So OCH3, OCH3, CH3. All right, there you go. That is hemiacetal, acetal, hemiketal, and ketal formation. Now, I could ask you to label what each of the things are, like which one's which. And so the way that you would do that is you would say, okay, remember, hemiacetals only have one OR group added. So this would be my hemiacetal. because I only have one of those groups there, and I have an H available to say that, oh, it was an aldehyde to start with. This would be my acetal, because there's the H. Down here I'd have a hemiketal, because I don't have an H there. Instead, I have the R group that was present, showing that it was on a ketone. And then this would be my ketal. Whew, all right, so we are due for a break, so I'm going to put the break timer up. When we come back, we're going to finish the rest of chapter 14, and then that's really all we're going to do today. I can't find my timer. There it is. What was that sound? Oh, it was a cat. My goodness. So we'll start the timer. We'll find the music, and we'll get it started, and we'll see you in just a little bit. Oh, I tried to like sneak an extra time in there, but I hit stop. Alright, we'll wind this down here. And excuse me. We will get back to work. Oops, that's not how we will do that, though. There we go. Alright, so all these reactions with alcohols are neat and all, but why do we care? And the reason that we care is because let's suppose that you had a molecule that had both of these features on it, such as, say, a long-chain carbohydrate. What ends up happening in this case is that if I take my alcohol group that is on the tail end of this aldehyde, I can do the same thing. And so I can say, okay, my O is going to go here, my H is going to go here, and then I break these bonds. And I make a cyclic compound. Guess what happens in carbohydrates? Da-da-da-da. This. Carbohydrates are usually 5-membered or 6-membered rings. In this case, we have a 6-membered ring. And when they do this, they make a very particular bond that closes the ring. And that bond is strong enough to keep the molecule in place because of the nature of this carbon right here. This is a special carbon. It's called the anomeric carbon. We're going to talk more about that in the carbohydrates chapter. But suffice it to say, if you do this cyclic reaction, then what you end up with is a product that is pretty stable. Now, they can still unravel, but they will tend to stay in this form more often than not. So it is possible to go back. They're not locked there. Now, an interesting feature is that this is a hemiacetal because I have an OH group here on my molecule. Remember that hemiacetals are reversible, but acetals are not. So if I were to take this molecule right here, here's my hemiacetal, and I react it with an alcohol, then I basically just swap out OCH3 for this OH, right? Because I would do this. I've never drawn it like that in this class, so I'm not going to do that now. So my H would go up here, and then the OCH3 would take its place. And I would get this as a result. Now, this is irreversible because this is an acetal. And that's going to have really interesting consequences for us later. So what we have here, over here we have a saccharide, or a monosaccharide because it's one sugar molecule. More on saccharides in the carbohydrates chapter. But on the right here, this group right here for my alcohol is just CH3, but it could be some other saccharide because I have an OH on this one. Why not just hook two of them together, right? You could totally do that. And so that's how you get disaccharides and polysaccharides. And you can put all sorts of these carbohydrates together to make a giant chain, which will eventually become pasta or a cell wall or fruit or sugar. All sorts of things are possible. So that's why we care about these hemiacetal, hemiketal type reactions, is because we're going to use this type of reaction to do chemistry to make carbohydrates. Carbohydrates. All right, so let's summarize what we can do with aldehydes and ketones. What did we learn that we can do? We sort of already knew that you could oxidize aldehydes into carboxylic acids, but we'll repeat it here. Can't oxidize a ketone. There's no H on the carbon adjacent to it to do anything with. We can reduce aldehydes and ketones. So if you take your aldehyde and reduce it with H2, you get a primary alcohol. If you do it with a ketone, you get a secondary alcohol. And if we use alcohols as reactants, we can get hemiacetals and acetals if we start with an aldehyde. And we can get hemiketals and ketals if we start with a ketone. All right. So that's our summary for everything we can do with aldehydes and ketones, which is a lot, it turns out. And there's still a little bit more left to talk about in this chapter. So if you have any questions, let me know. The last thing we're going to talk about is sulfur. I know, it stinks, right? Gross, sulfur. Sulfur's kind of smelly, but sulfur is also essential. Sulfur is one of the most important compounds in DNA because it does a very specific thing. Sorry, not DNA, proteins. In proteins, it does a very specific thing, and that is it forms a sulfide bridge. So knowing how sulfur behaves is important because it's going to pop up when we talk about proteins later. All right. A sulfur-containing compound is called a thiol. It's like an alcohol, except it has sulfur instead. So what that looks like would be something like this. And you can name these in exactly the same way as you'd name an alcohol, except it would be a thiol at the end of the alkane longest chain. So this would be 1, 2, 3, 4. This would be 3-methyl 1-butane thiol. So instead of butanol, you just write the name of the alkane and then write thiol at the end. No big deal. So that's pretty straightforward. We're not really going to do a bunch of examples with that, but the important thing to talk about for thiols isn't that they stink, but they really do. They smell very bad. If you pass gas and it smells like flatulence, I'm trying to professionally say fart, and I'm glad I found flatulence there. What you are smelling typically is hydrogen sulfide, which is a thiol. So you can think of thiols as like the pass gas smell. Like, ugh. If you've ever been to a sulfur pit, those are thiols. All right. 2 reactions that we care about for thiols. The first one is the important one because it's what we see a lot of. The second one is important because it's deadly. All right, so the first reaction we're going to do is an oxidation, and what this does is it creates a bridge. So if I take 2 thiols, I'm going to write the same thiol twice, just the mirror image of it. And I put an oxidizer in here. Here's what happens. My H's hang out with this guy, and then I make a bridge. And so this is called, literally, a sulfide bridge. I mean, it even looks like a bridge, right? It's got little S's there, and it makes a bridge. Now, this is going to be really important later on when we talk about proteins, because what proteins do is they're this really, really, really long chain of molecules that's almost like a polymer, except the repeating units aren't identical. Proteins are composed of amino acids, and some of those proteins have sulfur in them. So, for example, the cysteine amino acid. And those have this group on there. And so what you can end up doing is have this really long chain, and then it has, oh, this also has a cysteine on it. Let's oxidize it. And so then boop, boop, boop. And now what you do, or now what I have done here is I now have this molecule that is connected and is stuck in the shape. Why would I want my molecule to have a particular shape? And the answer to that is it makes my protein soluble in water so that it can move into other places. So a protein that is in a particular folding pattern, you might have heard of protein folding, has properties that correlate with the solvent around it, such as water, or maybe it needs to stay in a cell membrane, or so on and so forth. If you break this bond in some manner, then you change the shape and you would denature the protein. We'll talk about denaturing proteins when we talk about cooking in the protein section. In fact, a lot of the biochem stuff that we're going to talk about, I'm going to talk about cooking because I love to cook. Now, just like we said before, the opposite of oxidation would be reduction with platinum and H2. So if I did H2 plus platinum catalyst here to this thing, I would then turn it back into that. Which apparently I did on the bottom. I didn't actually expect that to appear. All right, so I can oxidize two thiols to make a sulfide bridge. I can reduce to remove the bridge. Now, the other reaction that we have is toxic. And so this is a bad reaction. We do not want this reaction to occur. What ends up happening is that if you have metal ions and they're exposed to sulfur, sulfur loves metals. It's like Maya and me. It just wants metals, like Maya wants pets. So let's suppose I have mercury. Mercury can find a thiol, and what it does is it makes its own little sort of bridge, but the shape is very different. It's longer, for example. The mercury ion is not inert, so it could come out of there and react with other things. It is an ionic bond, so the bond type is different. The electron density would be different. And this is bad. Now, because thiols typically do various biological applications, usually this is protein related and folding related. When you put heavy metals into your solution, you end up denaturing your protein. And if something is denatured, it doesn't work. Typically speaking, this is an application that you could do to potentially kill off like a bacterium or something, but the other way to denature proteins is much easier. You just heat them. Speaking of sulfur loves metals, Maya loves pets. Hi, Maya. I'm busy. So this is why mercury is toxic for you. Other elements that cause this, so lead does this. Oops, that's not my pen. So lead does this. Cadmium does this. Let me look at the periodic table and see if I can find more that would do this. They tend to be elements in the +2 oxidation state. You can hear Maya in the background if you hear. I just looked over the volume speaker. So you do not want metals in your proteins because they will latch right onto your thiols, and that's bad. So on the screen, I have two reactions that I want you to try. Tell me what the products would look like for both of these. Note that I've given you 2 of the thiol for each reaction. Draw the product, and we'll go over the answers together in just a second. Yes, you're beautiful. She's a very pretty cat. She's pretty annoying, but she's also very pretty. Maya hit the keyboard and deleted part of my slide. She's like, hey, you don't need this, do you? Boop. No. She's on my lap. 1 or 2 more minutes, we'll go over the answers, and then I'll put the cat away. Oh, she got off my lap. It's fine. I'm gonna guess that was Steve. Yep. Oops, I muted myself. All right, let's go over the answers here. So for the first one for my thiol, I'm going to draw the thiol. I'm going to mirror it. That's how I like to do these reactions. And then since I'm oxidizing, I'm going to oxidize by, here's my oxidizer. I'm going to take this H and this other H away. So I'll bust out the eraser here and go boop, 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 boop. And I'm going to make the sulfide bridge right here. I don't know why it's so big, but that's okay. And then for the lead 2, I'm going to do the same thing here. I'm going to put the lead right here. And what the lead 2 basically does is it shoos the H's away. And so the end result that I get here is I get rid of these. And mine's going to be a little bit crooked, but that's okay. And that's what I get. We don't really care about the inorganic product, so yeah, this makes an acidic mixture. But whatever. What's the important thing here is that if you add a metal, you create a metal inhibiting thiol bridge. I'm not actually sure if that's what that's called. But the metal inhibits the structure of the protein and causes it to denature. All right. Are there any questions about thiols? Let me know. There is one last thing that you have to do in this chapter, and that is celebrate. Because it's over. Hooray! Oh, my music stopped a little early there, but that's okay. There we go. Yep, all done. That's all I got. That's everything I have to do today, and that's everything that there is on the exam. So, there's still extra time. So if you have questions or at all about random stuff that could be on the exam, actually, let me just go back to here, I guess. We didn't even use this today. That's fine. I guess what we can do here is I could just do this. There we go. We'll just put it in the corner there. So yeah, there's 20 minutes left in the class, so that's all I was going to do today. Was I was going to finish the chapter. There's no reason I feel to start chapter 15, which is actually the end of OChem. We'll be done with organic chemistry after we finish chapter 15. But it's not going to be on exam number 1. After thinking about it last night for the exam, I decided that I'm just going to put the exam on Monday. And not have people vote on it because my other class, I sort of just unilaterally decided to do that anyway because of timing issues for other reasons. So I'm going to move your exam to Monday, which means that I'm going to put the Chapter 14 quiz online after class today. And then it will be due... I want to say it will be due Friday. And then you'll have one extra day to turn it in, which will be Saturday. So you won't have like a whole week to do the test or the quiz for this. Because when all the quizzes are received on Saturday, then I unlock it all on Sunday so you can see it. And then it's open for you to be using and reviewing from, and you'll have that information for the exam on Monday. So that's the intent, is that if I have the exam on Monday, I can still give you this quiz, you can still do the questions. You have 3 days or 4 days to do it or so. That should be enough time. And then you have a whole day to review that material specifically if you need to. That's the plan, at least. So, if you have any questions about that plan, let me know. I'll post an announcement after class once I've posted the quiz, also explaining that in a summary. So yeah, if you have any other questions, let me know. I'll leave this just going for like a minute or two, and if there isn't anything else, then you can always just email me your questions. That's totally fine too. Oops, I didn't mean to actually hit that. There we go. We'll just do that. Okay. Well, I guess then what we'll do is I guess we'll just call it a day. If you have any other questions, feel free to let me know. Either in Discord, send me an email. You can always take pictures of stuff and send me those pictures too. I realize you're drawing a lot of structures and it's hard to convey that information in text. Feel free to snap a shot of anything that you have with your phone or draw it in mole view and then send it to me, and then I'll try the best to answer your question. Otherwise, make sure to get in lab worksheet number 2 and quiz number 2 by the deadline tonight. Those are due. And have a wonderful weekend. Happy studying, and best of luck on exam number 1 coming up next week. So we'll just sign out with with this again. See you later.